When we're speaking about reactions with alkenes, it's very important to start noticing something about the double bonds and their properties. Let's start with a very simple molecule. If we begin with ethene and we look at its original, or how would I say, condensed formula, we have CH2, a double bond, CH2, which if I further expand, I'm going to get my two carbons double bonding with the hydrogen atoms on the side. However, what happens when we add an additional carbon, which is the case of propene? We're going to get CH2, double bond, CH, CH3. What does this mean? This central atom has less hydrogen than this edge atom of carbon that has two hydrogens. This is going to impact whenever we're adding different types of molecules because it's asymmetrical. In this case, when we have a double bond, just with between two carbon atoms here, we have a symmetrical amount of hydrogen on both sides. But here, when we have it right here at the edge, the amount of hydrogen is asymmetrical. This is relevant when we're adding asymmetrical molecules. What's an asymmetrical molecule? Fluorine is symmetrical because if we expand it, we have two atoms of fluorine. Chlorine is symmetrical. We have two atoms of chlorine on both sides. However, when we add an acid, hydrochloric acid, hydrofluoric acid, even water, which could be an acid or a base, we have asymmetrical molecules. Hydrogen and chlorine, hydrogen and fluorine, hydrogen and hydroxy. How does this all come together? There's a rule called Markovnikov's rule. So Markovnikov's rule states that when we're adding asymmetrical molecules, we have to analyze the double bond to determine what atom goes where. And it is as follows. In this example, let's take propene and we're adding an asymmetrical molecule such as hydrochloric acid. There is only one result possible. Let's analyze this molecule. How many hydrogen atoms are on carbon number 1? Let's number this. On carbon number 1, there's 2 hydrogen atoms. And on carbon number 2, there's only 1 hydrogen atom available. Let's expand this so that it's clearer for you guys when you're looking at the video. CH2 double bond, CH, and then CH3. Okay? So this is obviously the central carbon, which is carbon number 2, has less hydrogen attached to it. So Markovnikov's rule says that hydrogen is always going to go to the original carbon atom that had more hydrogen in it before the reaction. So in this case, which atom has more hydrogen, 1 or 2? Obviously, number 1 has more hydrogen. Therefore, if hydrogen wants to go with its friends where you have more hydrogen, the chlorine atom or the other atom that's not hydrogen, or the other piece that's not hydrogen, is going to want to go to the carbon that has less hydrogen. So in this case, our only possible answer is the chain. We broke the double bond, and at number 2, we're going to attach our chlorine, because chlorine is going to attach to the atom that has less hydrogen, and hydrogen went to the carbon atom that had more hydrogen. Let's look at another example. And again, don't be intimidated by the molecule or the size. Always look for the double bond. When we add a water molecule, remember this water molecule can be viewed as HOH. We look at our double bond. So I'm going to redraw the structure. And the issue is, what's going to happen to this OH? So carbon number 2, how many hydrogens does it have? Carbon number 2 is making 3 bonds. 1, 2, 3 to the other carbon. So it only has 1 hydrogen atom, which I'm representing with this dot. And carbon number 3 is double bonding here, single bonding to the top, and 1 single bonding to the right. So this is bonding 4 times already. This has no hydrogen in it. So again, the rule says, Markovnikov's rule says that hydrogen goes to where there's more hydrogen, and the other side of the molecule goes to where there's less hydrogen. In this case, 1 and 0. So our hydrogen atom goes here. We broke the double bond, and then our OH group goes in the middle, and this is the only answer. Markovnikov's rule is especially important when we have the addition of asymmetrical molecules to double bonds where we have asymmetrical amount of hydrogen atoms.